Okay, so I want to start. Last week we started developing a path integral representation of a theory of bosonic particles. And let me just remind you where we arrived at. So this technique is called coherent states path integrals. And the idea is that we define coherent states, which are eigenstates of the annihilation operator with some complex eigenvalues psi. And the same we also have for a dagger with a psi bar. And what we showed last week is that we can write an expression for the partition function, right? Take your seats. We can write an expression for the thermodynamic partition function as an integral over multi-component, a path integral over the field psi. So this is where we got last time. First of all, we have a set of fields that are defined as the local function of an imaginary time tau, and they have an index alpha, which is some kind of quantum number in terms of which the bosonic states, the single particle states, are defined. And I remind you that we are doing everything for bosons for now. Actually, today we will see how to generalize it to fermions, but let's first continue with the bosons. So for bosons, we have the commutators of A and A dagger, and the coherent states are defined as eigenstates of the annihilation operator, and the psi fields are complex. Okay, so basically A and A dagger are replaced by psi and psi bar, where psi bar is the complex conjugate of psi. Okay, and now these psi's are no longer operators. They are really complex functions, and they depend on two variables. One is a continuous variable tau, which is defined as an imaginary time direction, and alpha is the index, and it can also be continuous depending on what is the basis of single particle states you want to work with. Okay, so then what we found is that the partition function, which I remind you is generally defined as a trace over the Boltzmann factor, where H grand canonical is the Hamiltonian operator minus mu n, where n is the total number operator. This is in a grand canonical ensemble, which is for field theoretic description of particles, is better. It's more convenient because particle number is not necessarily conserved. Okay? So let me write down what we we got last week. That's how we ended the lecture. We can represent z as the path integral over e to the minus s, where s is a functional of the field psi and psi bar. And when I'm writing psi without any indices, what I'm referring to is, let me write it on the side. So what is psi? Okay, this is an implicit way of writing something that is actually an array of variables, of complex variables, which again they depend. So alpha is an index. It can be an infinity array or a very long array of states, but it's actually an array. Okay.
Psi is the eigenstates.
Psi are again these are the coherent the eigenstates of the annihilation operator, but they are just complex fields. Okay, they are complex numbers that are functions of tau and of alpha. Okay. Okay, so what are the definitions here? First of all, let us define this differential. And I forgot to write here something. So I'm integrating over all the possible values of psi of tau, where I have a constraint of periodic boundary condition in the imaginary time direction. So psi of 0 equals psi of beta. And I also remind you that throughout this whole lecture, we work in units where k Boltzmann and h bar equal 1. So beta is the inverse temperature. Okay? That's the same beta that appears here. And in these units, beta has dimensions of time, right? Because frequency, temperature and energy are all the same. Okay, so this D is defined mathematically as a limit when n goes to 0 of a product over j going from 0 to n d psi bar divided by, sorry, this is there's a product over alpha of d psi alpha bar, d psi alpha over pi. Okay, and here j in the continuum limit, when you take n to infinity, our definition of the continuous variable tau is just j times d tau. Okay? Okay, so j is the discrete time step. However, if we take the number of steps to infinity, it's like taking d tau to 0, and then instead of just a discrete index j here, you have a continuous variable. Okay? So formally, if you want to define a differential, which is a product of the differentials of the individual components, you have to write it like this. Okay? Okay. So this is the differential. Now, this is the definition. And what is S? Yeah?
So alpha is the...
Alpha is all the time our notation for a quantum number.
And J is the number of the particles.
No, J, again, so we have, the idea is that we have an imaginary time axis. Okay, this is how we do the path integral. We start from 0 to beta, okay? And this is analogous to propagation in time, except it's not a real time, it's an imaginary time. Because we have here a real exponential, but the way we develop the path integral is to divide it to very small steps of size d tau, and j is the index, okay? So this is j equal 1, 2, 3, okay? And j times d tau is just like an equal time step, okay? Gives you a continuum.
This is the same J.
So this J is, so if I'm, for example, parked at some arbitrary tau here, it corresponds to some J step, where tau is J times d tau, and J runs from 0 to n. Okay?
This is the same J in
the same J, yeah. This J is this J. Okay? But when I'm writing, that's the thing, in the continuum limit, let me also write this just to remind that psi alpha j in the continuum limit, and the continuum limit is n going to infinity, the tau going to 0. Okay, it's the same thing, okay, just shrinking the step. The continuum limit of psi alpha j is psi alpha tau. Okay, with the identification that tau is just j times d tau. That's all. Okay. All right. So now what is S? So the result we got last time is that S is written as an integral from 0 to beta over d tau of the following expression. It's psi bar d tau psi plus h of psi bar psi minus mu psi square. Okay? Or actually, let me write it, although it's identical, I prefer to write it like this. Okay? Psi bar psi, which of course for complex numbers it's just absolute value squared. But I want to keep it like this. You will see why, because then when we get to fermions, it has a different meaning. Okay? So now when here, implicitly again, whenever I'm writing psi here, it's actually psi of tau. It's psi of tau, or psi of tau is an array of numbers. Okay? It's not just one complex number. And when I'm writing this, it's implicitly summing over all alpha. Okay? So let me write it on the side just to remind. This is psi alpha 1, psi, it's actually this times d tau of okay, which is a sum over alpha, psi bar alpha, beta, psi alpha. Okay?
Scalar.
Yeah, it's a scalar product. Yeah, so it's a scalar product over the indices alpha. Okay? Okay, and similarly, what is h of psi? And h of psi is just a functional of these fields of psi and psi bar, which has the form, you just take the Hamiltonian written in second quantization, and every time you see an annihilation operator, you erase it and write psi. Every dagger you replace with a psi. Okay? That's the notation. Maybe we can write here an example. Okay, I'll write it later. I'll get to it later. But actually, let me write it here. So h minus u is something that you can write as the Hamiltonian is a sum. This is the most general expression is a single body part. Actually, it's not the most general expression, but it's the characteristic Hamiltonian we want to deal with, which is you have some single body and a two-body interaction term. And this is the single body in an arbitrary basis, okay? And here we have an interaction term that is the sum over 4 indices, V, alpha, beta, gamma, delta, psi bar, alpha, psi bar, beta, psi, gamma, psi, beta. Okay, something like that. Okay? Well, and every time I write psi without any argument, it's actually psi of tau. Okay. So, and then the last term is to be written explicitly is the sum over alpha of psi bar alpha psi. Okay. All right. So that's what you have in the action, and this thing you put in the exponent, and now you want to ideally you want to solve an integral, okay? And it's an integral over multiple variables, in fact, infinitely many variables, right? Because you have to take the limit of m going to infinity here. But when I write it like this, you see that the most complicated problem here, as you'll see soon, is the interaction, okay? If there is no interaction, if v equals 0, there is a good chance that the integral will be solvable. Why? Because if the Hamiltonian is completely quadratic, it's just bilinear in psi and psi bar, then it has the form, the integrals that we have to solve have the form of Gaussian integrals. And for that we know how to solve. There's a formula, right? And in fact, we could then simplify the problem by choosing a basis where the single body term is diagonal, and then it will even decouple, okay? This is the ideal gas problem that you are familiar with from StatMech. In fact, we did such calculations. But, and the interaction complicates it, but even if we have zero interaction, there's still one step we want to make in order to make this theory tractable, and the problem is the first term. The first term is the only term here that is not local in tau. It has a derivative, right? It has a derivative And when you see a derivative, it suggests that what should we do to exactly? We go to Fourier space, and we define a Fourier expansion of psi of tau, which has the following definition. There's some normalization factor here. A sum over n are integers, all integers of psi n e to the minus I omega n. Okay, this is a Fourier series. Okay, not a Fourier transform, a Fourier series, where what are these omegas? These omegas are, in fact, 2 pi over beta times n, where n is an integer. Okay, now why is this correct? So usually when you go to Fourier space, you do a Fourier transform, right? You go from tau to omega, with omega being a continuous variable. Why I'm going to a Fourier series and why this particular form? Because of the boundary conditions. Okay, so our fields live on a cylinder, okay, or hypercylinder, almost, because space dimension may be larger than 1, but this imaginary time axis is periodic. It goes from 0 to beta, and it's periodic. It's on a circle. Because of that, the function psi tau, in order for it to satisfy periodic boundary condition, it must have a discrete set of frequency. There's a basic frequency, which is nothing but 2 pi over the period, right? Beta is like a period. It's like a time period. So omega n are integer multiples of a basic frequency. Okay. Now this frequency, this set of frequencies, which I can also write as if I remember that beta is 1 over t, I can also write it as 2 pi n times T, where T is temperature. Okay? This set of frequencies are named after Matsubara. They're called Matsubara frequencies. So this is in the Fourier expansion, and
I get why what I don't get is why those frequencies specifically. Like why are
you have a periodic function. I'm reminding you of physical 2, 3, I don't remember which course you learned it, but any periodic function with period beta, in our case beta, don't get confused because T is not time, it's temperature, it's actually the inverse. So when you have a period in time, any periodic function can be expanded or must be expanded in the Fourier components, where the only frequencies that obey the boundary conditions are 2 pi over the period times an integer. Okay, why is that? Because when you can easily see that when you substitute tau equals 0 and tau equals beta, you get the same thing. Right?
So the periodicity comes from the
periodic boundary conditions. Okay?
No.
Very important.
Yes.
Okay. Okay. So So that's this is psi tau. Now you can of course write down the inverse transformation from psi tau to psi n, and it's written as an integral from 0 to beta psi tau e to the plus I omega tau. Okay, this is just the inverse transform. Or if you like, this is the definition of the Fourier components. But for our purposes, we have a functional written in terms of psi of tau, and you want to plug in this expansion, and you see that it gives you let's see what it gives. I want to focus on this term, okay? The term psi bar d tau psi. Let's see what it gives, and you can easily see that it will. This I can erase now. Okay. So let's do it quickly. So what I'm doing now, I'm plugging in for psi of tau. I'm plugging in this expansion, and for psi bar, what do I have to do? I just a complex conjugate of this, so it will have psi n bar. And this will change sign, so let me write it down explicitly. You get 1 over beta, and then there is a double sum over n and n prime, okay? First you have, let's write down the expansion for the psi bar, so it's psi bar e to the I omega n prime tau. And then I have a time derivative of a sum over n, psi n e to the minus I omega n tau, right? Now, okay, now the time derivative acts only on the exponential. What does it do? It brings down a factor of minus I omega n. Okay? So I'm going to get 1 over beta, double sum. Sorry, here I didn't write it carefully because the sum is here, but I can change the order of the summation, right? The sum over n prime, psi n prime, minus I omega n, sorry, this is with a bar, psi n. This is after I took the derivative, and then what I'm left with is e to the I omega n prime minus omega n tau, right? Very good. So this is still a function of tau, but notice that in the action I have to integrate over tau from 0 to beta. Okay, so the integral over tau from 0 to beta of psi bar d tau psi will give me 1 over beta, sum over n prime. Okay, I'm just copying it. And now I have an integral from 0 to beta of this exponential function, right? Where, remember, the Matsubara frequencies are just integer multiples of 2 pi over beta, and the integration is from 0 to beta. right? So what is the result of this integral? I think you can easily see that
Good alpha.
it vanishes if n is different from n prime, right? And if n equals n prime, the exponent is 0 and you just get a factor of beta, okay? So this integral gives this gives beta delta n n prime, okay? And therefore, when I plug it back into the summation, the double summation over the dummy indices n and prime, because of the delta, give me just one sum. Okay? So, in other words, what I'm getting here is, after integration, I will simply get a sum over n of psi bar n psi n times a factor of minus ln. Okay. Now I can also do the same for the Hamiltonian. The single body part, this one and this one, when I plug in the Fourier transform, will also give me a simple sum. So let me write down what we get if we do the non-interacting case, okay? So the interaction, we'll deal with it later, okay? But if we have non-interacting system, okay? So this is for V equals 0, okay? For V equals 0, that's where the Hamiltonian is just single body, and we therefore, let me write it here. Let us choose the okay, actually, let me write the most general thing. So the Hamiltonian will now be just a summation over, some single body parameters, psi alpha bar, psi beta, but we can always choose the basis to be diagonal, okay? And this is we call it H0, okay? This the non-interactive part. So for a non-interacting case, which is okay, what this means, okay, it's free bosons, an ideal gas of bosons, if you like, okay? Then we get that the partition function, and I denote it as Z naught to represent the fact that it's non-interacting, okay, is going to be just this times e to the minus s naught, where s naught is now the following expression, very simple, sum over n psi n bar minus I, okay, let me actually write it more explicitly. So I'm choosing a basis where H is diagonal, okay? And then that's what I get. It's plus epsilon alpha minus mu times psi n. Sorry, so this is, these psi's have two indices. In this representation, I also sum over the components alpha. So psi has two indices. N represents the Fourier component, and alpha is the quantum number that we keep all the time. Okay?
What happened with the integration over dt?
Hmm?
D tau. What happened with the integration of
The integration is what gives you, and again, I did it explicitly for
it
this
was the
term,
first term, but we also
but
have
the second term will be exactly the same. Okay, you can repeat the calculation. It will be even simpler because then I don't even have to apply a derivative. Okay. So if I have a term, if I take a term, okay, it's exactly the same calculation. Okay. It will be less trivial for the interaction term. That's why I'm focusing now on the free boson space, okay? And another simplification is because I have no interaction, I chose the basis so that this is diagonal, okay? So here I chose epsilon alpha beta to be in a diagonal basis, okay? And for any case of free bosons, you can choose a set of quantum numbers where the Hamiltonian, the single particle part is there, okay? So what did we get? If you look at this expression, it's actually very simple. Because all the stuff in the, sorry, I have here another parenthesis that I forgot. Okay. So all the stuff in these small parentheses is just a number, okay, that depends on, it's a complex number actually because there's a minus I omega. It's a complex number that depends on two indices, n and alpha, and it's diagonal unit, okay? So it has the form of a scalar product of with some number of front, and I think you can easily recognize that if I now plug it into the exponential, I notice that S naught is separable to an independent sum of terms for different n's and alpha. Okay? Okay, it separates to, it's a sum over all n's and all alpha of something. Okay? And the exponent of a sum is a product of exponentials. And what I get is, now remembering that this differential is actually also a product of differentials, I just have a product of independent Gaussian variables, okay? So let me write down here a formula that we are going to use. Yeah. Okay, so let's write it somewhere there. This. I just want to say there's one little, not very subtle, but something you have to be careful about. So when I defined my differential, I defined it in terms of psi of tau, okay? Now I change variables from psi of tau to the Fourier components, which is okay, it's a linear transform. It's a change of basis, but I have to take care of the measure so that eventually the partition function has to be a dimensionless quantity, right? And psi n, if psi tau, let's say, is a dimensionless, psi n has different dimensions. You see it from here, right? There's an overall factor of square root beta between them. And if I have a bilinear term, there's a factor of beta, okay? So this differential, if I want to write it in terms of the Matsubara components, it has to be written as a product over n and alpha of d psi bar n alpha, d psi n alpha divided by pi, but there is also a factor of beta. Okay? This just maintains the dimensions, okay? It's the same differential, I just write it in terms of the Fourier components. You see now it's very convenient because n naturally is an index, a discrete index. I don't have to take the limit, okay? And all that. It's a discrete index, and the reason that it's discrete, just n is all integers, is because of the periodic boundary conditions, okay? Because I have a discrete set of Matsubara frequencies. I want to write this formula down here because we want to keep the definition. I mean, we'll need it soon, okay? So now I think I can erase this. Okay. All right. So let me now write mathematical formula, but this is the mathematics that we need. So Z naught, which is my notation for a free particle, can schematically be expressed as a path integral with this notation of something that I can schematically write as psi bar A psi. Well, this is implicit for, let us write, A is a big matrix, okay, with many indices. This is just a short notation for, sorry, I forgot the minus sign, of course. I forgot the minus sign. So this is sum over n alpha beta psi bar n alpha. This is very general now. What I'm writing here is general, not necessarily in the diagonal basis. A is some matrix, okay, and it has indices n. Sorry, n, where's my, this is n alpha, beta, okay. So n is the same n because it's all diagonal in n, as we saw. This is because of the integration over tau, and this is what it is, okay? Okay, but when I write it like this, it's implicit. Psi are vectors, like very big vectors, and A is a matrix. And the result of this is a mathematical formula that you will prove in your tutorial or the homework, but it also appears in the books. You can prove that this is given by the determinant of a to the minus 1. Okay, and this is up to a factor of, okay, it's true up to a factor of 1 over beta to the n. Okay, there's some normalization factor that comes from this 1 over beta. Okay, this is a closed formula. Okay. Not get confused, I will write down this. Okay.
What is n?
N is, okay, it's because when I'm writing it like this, there's a product over n and alpha, and there are, I don't know, some number of terms in the product, and the factor of beta is multiplied by this factor. Okay, I don't want to write it explicitly because now it depends on the choice of basis. What is it? Okay, but we just have to keep it in mind. That's where it's coming from. Okay, because ultimately what I have is actually a product of many independent Gaussians, and the number of terms in the product, each of them has to be divided by beta. Okay? So it's some kind of a normalization factor, but the important thing is that the result is a determinant of the inverse of this matrix, whatever it is. Okay, that's completely general. Okay, how do you prove it? I mean, you can prove it. You'll do it in your homework, I think. But the way to do it is always to go to the diagonal basis, and then it's trivial. Okay. All right. In fact, okay, for the diagonal basis, so if we do have epsilon alpha is diagonal, then what we get here is that Z naught is just, what is the determinant of diagonal matrix? Just a product of the diagonal terms, right? So it's just a product over n and alpha of, and now notice that it's the inverse of the function. But what is the inverse of the function? So in our case, when I'm writing it like this, what is the matrix A? What is the matrix A, or the elements of the matrix A? They are just these things, right? This is this expression is A and alpha. Okay? It's a diagonal matrix.
But this is a very simple case.
That's right, but you can always show that, so that's right. So if it's not diagonal, you cannot write a simple expression, okay? But you can find another basis. But if that's what you have, right? Generally, if you have such a thing and if epsilon is not diagonal, you change basis.
Even if it's diagonal, basically speaking, so we'll have like a higher dimension matrices.
The matrix can be infinite.
Yeah,
in fact, it is.
What I'm trying to say, it's a tensor, like not only
No, it's not a tensor. It's not a tensor. It's a matrix.
But what if we have further complication in the indices, for example?
We don't have it if we have a non-interacting problem.
Never?
No, I mean, formally, the interaction term is something like that, right? Because it depends on 4 indices. But it's not something you can solve.
But it's
So
not relevant for that.
it's not, first of all, it's not relevant for that because we set it to 0, right? But if you, let's say you have it, okay, I can write it as a tensor, sorry. I can write it as a tensor, I can call it a tensor, but I don't know how to solve the integral. Here I can tell you what is the result. Okay, in the end, the partition function is a physical, or actually the log of the partition function is already a physical quantity. It's the free energy, right? I can compute it. So let's do it. Okay, I mean, I will not do it through the end, but you'll see in one line we get something you already saw in undergraduate studies. First of all, just formally, the determinant of such a diagonal matrix is the product of the diagonal terms, but notice it's not of A, it's of A to the minus 1. Okay? A to the minus 1, if these are the diagonal terms of A to the minus 1 is just 1 over this, right? So we can write it like this. And don't forget the factor of beta that comes with every term, minus I omega n plus epsilon alpha minus u. Okay, that's all. Or, if you remember that beta is the inverse temperature, it's a product over n alpha of T divided by minus I omega n plus, okay? So this is a closed exact expression for the partition function of 3 bosons in the basis of, in the diagonal basis, okay? Okay, but this is partition function. We want to notice, by the way, that it's indeed dimensionless, right? Because temperature and the frequency, all of these have the same unit, so you get it, it's good. Now let's compute, or not compute, write down a closed expression for the free energy. What is the free energy? And I call it F naught. It's minus T log of Z, right? That's a definition. Remember definition of the free energy. Remember that? Okay, good. So what is it? It's now I have to, so there is a factor of minus T. Now the log of a product is a sum of the logs, right? Okay, so it's actually a sum over n and alpha of, now it's the, actually, sorry, let me just,
The
yeah,
minus should
right,
cancel out.
so it's because of the, so because it's in the denominator, so first of all the log of t will give you just some constant, something that does not depend on the energies. It's not interesting, but what you're going to get is a log of this. And the minus sign is actually cancelled because it should be minus the log, right? Because this appears in the denominator. Now, this already, I think, starts to appear familiar, or it should be, but not quite. There is still a problem. You need here to perform the summation over n, okay? And there's a way to do it, which you'll do in the next tutorial, next week. with SAR. It's called the Matsubara sum. Okay, so remember, what are the omega n's? This is the only thing that depends on the index n here. And omega n is an integer multiple of something, of the basic frequency. And you have to sum an infinite sum over all integers. Okay? There's a trick how to do it. And if you do it, I'm not writing the result, you will get, surprise, surprise, what you learned in statistical physics for ideal Bose-Gas. Okay? Now, another thing you can do with it is the following. So this is for the free energy. Another physical thing that we can calculate is the occupation number of bosonic particles in a particular state alpha. What do we expect to get, actually? Okay, without doing any calculation, let's see if you remember. I have an ideal gas. Okay, alpha is just the quantum number, it may be momentum or whatever. I have an ideal gas of bosons. What is the occupation of a state alpha, any quantum state, in finite temperature and finite chemical potential mu? Or how do you call the function that describes it? You don't remember? Okay. It's the Bose-Einstein factor, right? So in fact, you can get it from this, and it's a very simple calculation. I mean, simple under the understanding that you learn how to do Matsubara sums, but as I said, there is a simple formula. Yeah, you wanted to ask?
Yeah, so it means that the Bose-Einstein formula is only applicable when there are no interactions.
Yes, exactly.
Like always,
Exactly, that's completely right.
and then you
Right.
have motivation.
Yeah, it has to be an ideal gas. And in fact, actually for that reason, so if you put interactions in a bosonic system, they always have a very dramatic effect. I mean, they change the nature. And experimentally, when Bose-Einstein condensation in cold atoms was first discovered and received the Nobel Prize, the first challenge was to prove that it's really by the book, the Bose-Einstein condensation by the book, which assumes an ideal gas. Okay, and the ideal gas assumes that the interactions are zero. It's not so easy to have a system with zero interactions. So it has to be dilute and still condense. Okay, that was a challenge to prove it. Okay. In any case, okay, so that was just a side comment, but now to get the occupation, I want to define another quantity. So, and this is called a Green's function. Okay, so I define it as follows. So the Green's function is going to be, there's going to be some matrix that I denote by G. Okay, this is notation for a matrix. Okay, so the n alpha, n prime, beta element of the matrix is defined as the expectation value of psi n alpha bar, psi n prime beta. Actually, let's not call it beta. I call it alpha. Okay, that's a definition. Okay. Now, what is the definition of expectation value? It's just like write it on the side. For any functional O, this is defined to be the integral d psi bar psi e minus s O. Okay, normalized by the particle. This is a general definition of expectation value, or a thermal expectation value of any physical quantity or any combination of fields. Okay, it doesn't have to be necessarily a physical quantity. And in particular, if we want to compute this, the definition is that I have to integrate over psi bar psi, okay, minus s, psi bar n alpha psi n prime alpha prime divided by z. Now, this is a general definition, first of all. This is just a definition. But now if we look at J naught, okay, the naught always defines non-interacting, okay, the ideal gas case. So this is the same thing in psi n prime alpha prime computed in S naught, okay, so it's e to the minus S naught of the same thing divided by Z naught. And since, again, S naught is quadratic, okay, this is given by the expression we just calculated, but this integral is also a Gaussian integration, right? So there's another formula. I'm not writing it here, but it's just the generalization of the formula that you're familiar with. For real numbers, you get something like that, right? And if you normalize it, you just get 1 over A, or actually pi over A. Okay, never mind, but there's some normalization factor, but you get just the inverse of whatever appears here in the exponent. If you do it for multiple variables, you can show that this equals, let me write it down here, a delta of n prime, a delta of alpha prime, times the n alpha diagonal element of the inverse matrix. Okay? So, because of that, when I'm writing S naught schematically as psi bar A psi, where A is again some matrix that can be written in a diagonal basis, it can be identified with the inverse of the matrix G naught. Okay? So again, the matrix element of the Green's function is a matrix element of the inverse A, where A is whatever appears in the exponent, and therefore A is the inverse of G. Okay? So this object, which are the diagonal elements of A, are 1 over the diagonal elements of the Green's function. Okay? Right? This is clear? Okay, so let me put this in a...
The Green function is equivalent to the A matrix, the inverse A matrix.
Yeah, exactly, right. Here I just prove it for individual elements, but it's generally G, the matrix G, or G naught, okay, again for a free theory, G naught is the inverse matrix of what I called A, okay, which is defining the quadratic action. Okay, very good. So now let's, why did I define the Green's function? First of all, it's important to notice that a lot of physical quantities can be expressed as expectation values of some combinations of psi and psi dagger. For example, suppose we want to treat the interaction perturbatively. What do we have to do? To compute to leading order, it will be an expectation value of a product of 4 such fields, right? And you can actually use a Week's theorem to, again, it's exactly the same mathematics. You can divide it to products of Green's functions. Okay, so the Green's function is a building block of a lot of expectation values of physical quantities. But let's not jump ahead. We are still in the ideal gas case. Okay, so in the ideal gas, we can use the Green's function to compute occupation. What is occupation? Where shall we write it here? Okay, and I'm really focusing on the diagonal basis. The occupation number is how many, we want to know how many bosons are in the state alpha. Okay? Now what is the definition? We take the, in terms of operators, this is what we want to compute, right? I'm now back to second quantization. I want to compute this thing. But when I convert it to path integral, the A alphas and the A alpha daggers, they become just psi and psi dagger, or psi and psi bar. So using a path integral notation, here I forgot to put the 0. So in the path integral notation, I have to write it as okay, something like that. Sorry, this is alpha. And I deliberately I introduce here the local time tau, but the result of this does not depend on tau. It does not depend on tau, because how do I know this? Because now I'm using the Fourier decomposition, which I erased, so let me just remind that this will no longer be. Psi of tau is sum over n, psi n, e to the minus I omega n tau, right? This is the Fourier decomposition. If I plug it here, I see that, and I use the fact that these expectation values will give me only diagonal terms. I have here the deltas, delta over L and delta over alpha. You can easily convince yourself that this will result, where is it? Yeah, this will result just T times the sum over alpha of G naught N alpha. Okay? That's what you get. Okay? All right? You have to work it out. Let's not jump into the head, but notice that there is no tau dependence here. Okay? I can write it as a local field, but when I plug in this notation, because of the delta on n and n prime, the exponentials cancel, right?
Should it be sum over n instead of alpha?
It's sum over, sorry. Yes, sorry, that's a typo. Yeah, of course, thank you, right? Yeah, no, it's for, so it's for particular alpha. Yes, of course. Sorry, that's very important. Yeah, it's a sum over n. Okay? So that's what it is. Very simple, but we also know what is G naught of n alpha. It's the inverse of this stuff in the action, which is this minus I omega and so on. So let me write it down. I have a factor of t here, and then sum over n of 1 over minus I omega, so omega n plus epsilon alpha minus mu, and the last part I have to do is to sum over n, where n is, again, it's an integer going from minus infinity to infinity. This is a Matsubara sum, and it's actually a very simple sum. I'm sure that you can find online a closed formula for it, because these omega n's are just integer multiples of something. But notice the most important thing is that it depends on the temperature. Okay, the result depends on the temperature. Actually, when the temperature goes to 0, the discretization becomes smaller and smaller, and in the limit of 0 temperature, the sum over omega n's can be converted to an integral, right? So you get something like a pole integral, but let's not go to t equals 0, because you can show, and this is okay, exercise that you will do, either Sar will do or you will do in homework, but it's an exercise in a Matsubara summation. What it will give you is exactly 1 over e to the beta epsilon alpha minus mu minus 1. And this is the so-called Bose-Einstein formula, or Bose-Einstein distribution. Which, again, if you work out what happens to it as a function of the temperature and mu, there is a phase transition in the ideal Bose gas to a condensate, which is the Bose condensate. Okay? Okay, so great. So the conclusion for what we've done here is, if we have a free theory a free theory meaning quadratic Hamiltonian, and therefore a quadratic form of the action. All we need to do to exactly solve for any physical quantities we want. We can also get, once we have the free energy and density, we can compute equations of state, we can compute specific heat, compressibility, whatever you want to know about the system. You can exactly calculate it. All you need to do is to find a convenient basis where the action is diagonal, not only quadratic, but diagonal. And then you have the final result, okay? Okay, what's the problem with the interaction? Why are the interaction complicated, okay? So let me show you what happens with the interaction. And one thing that simplified our calculations since the beginning of this class was that we saw that this term with the time derivative, which is non-local in time, can be converted to something diagonal in n, okay? It was something of this form, okay? It was diagonal in n, and that's true as long as you have a quadratic form. What happens if and the same was for the part of the free part of the Hamiltonian. But the interaction will no longer be diagonal in n. That's only one of the complications, okay? So let's see what happens to it. Okay, we have to erase some things. I think we can. This. Okay, so yeah, let me just write down that this form is schematically written as okay, so now what happens with non-zero interactions? Let's look at the interaction term in the action. So S is S naught plus, let's call it SV, okay, the interaction part, where SV is again, it's a functional of psi and psi bar, which explicitly can be written as integral from 0 to beta of, and now we have this 1/2 sum over alpha, beta, gamma, delta. There are some coefficients, and then we have our fields, and we have 4 fields in general. All of them are in the same tau, okay? Tau is just a time step, so they're local in time, but there are 4 different indices, and you see, anyway we choose our basis, we never get something diagonal because it's not quadratic. But now you say, okay, I will now plug in this Fourier expansion. Okay, let's do it. So I'm getting, first of all, let's do it carefully. Let's get out the sum over alpha, beta, gamma, delta. I want to keep the integral, though, and I also take out these coefficients. They're just some interaction coefficients. Now, what do I have to solve? I have to solve for integral over tau of the product of 4 local fields. And each of them I write as an expansion in n. But because I have 4 fields, how many summations I have? 4, right? N1, N2, N3, and 4. Altogether, I'm going to add a summation over N1, N2, N3, N4 of psi bar, N1 alpha, psi bar, N2 beta, psi N3 gamma, psi N4 delta, integral d tau of, now I have to integrate over the exponents. So what is in the exponent? I have I omega n1 plus omega n2 minus omega n3 minus omega n4, all that times tau. Okay? And I forgot a factor of, let's see, what the factor of 1 over beta squared, right? Because I have square root beta for each 4 times, okay? Okay, so this is actually 1 over 2 beta squared. Okay. Okay, now here comes the problem. If I look at this integral, what does it give? Exactly for the same reason before it also gives a delta, right? Because all these omegas are integer multiples of 2 pi times t. So this gives me a delta of, the delta only constrains one of the indices because the summation, so n1 plus n2 minus n3, n4 has to be 0, right? So this gives me a factor, first of all, it will give a factor of beta, okay? Then there's a delta of n4 with n1 plus n2 minus n3, okay? And therefore, it only reduces the sum over 4 indices will reduce to 3. Okay, so I still have 3 different indices of the Matsudaras, and generally also summation over many indices of the quantum numbers. Complete mess. Okay, of course you can have some very special cases and so on, but you can see that going to the Matsubara representation doesn't help. Okay, actually there's also a physical meaning to it, because these Matsubara frequencies, although it's kind of a mathematical trick, but there is, if you do analytical continuation from this problem to real time, they become real frequencies. Okay, they become real. I omega, if you do analytical continuation from imaginary time to real time, you get the same problem in the time domain, and then these are real frequencies. And the interaction, what it does is it creates interactions between which mixes frequencies, right? So it's a process of scattering where you should obey conservation of energy, if you like, and you are creating an excitation, right? That's what interactions do. You have a collision of particles with two different frequencies, the camera with two other frequencies, and only the total energy is concerned. Okay? So interactions are complicated. So what do we do with them? Either we have some special model that is exactly solvable, very rare, or we do perturbation theory. But the nice thing is about perturbation, about path integral, is that we can do perturbation theory and we don't need to stop at the leading order. Okay? So before we switch to path integral, when we looked at the second quantization representation, we saw that one nice approximation we can make is mean field. Mean field is equivalent to first order perturbation theory. In a path integral, we can actually expand to any order you like, and at least order by order, you can complete the corrections. So first of all, you can see if it converges. Sometimes, miraculously, it will converge to an exact result. And I'll show you an example next week. Okay, this not for today, but generally we want to be able to compute it, and we can get more information, not just the main field, but also some corrections that are very important, okay, that have interesting physics in them, and they can also be an indication that, for example, the system undergoes a phase transition. Okay, so okay, so let me just finish before we go for a break. I'm going to actually, you know what? Let me not do it because this will come later. Let's take a half an hour break, and after the break, we'll talk about fermions. Okay?
עכשיו אנחנו נכליל את זה לפרמיונים?
כן. Okay, so let me start. They're coming. So now let's talk about fermions, and first of all, we have to see what is the problem, why things are a little bit different, and we'll find a way to overcome it. So for fermions, we once again go back to our basis for many-body field theory. We have a set of creation and annihilation operators, A alpha dagger, but the difference is that they obey anti-commutation relations, and for that reason, you find that, so what does it mean? So if we have two different indices, A alpha, A beta, is equal to minus A beta, A alpha. So every time you do an odd permutation of the operators, you pick a minus sign. That's one thing. Let us also introduce back this index zeta, because in the end we're going to have generalized formula where zeta is a parameter. This is for bosons and this is for fermions. Okay. So first we have this signs for each odd permutation, and the special case of that, or one of the consequences, is that A alpha squared is identically 0, right? So we can immediately see that if we now try to generalize the concept of a coherent state for fermions, we run into problem. Why? What is a coherent state? Coherent state is defined as an eigenstate of the annihilation operator. Okay, that's what we did for bosons. Let's try to do the same for the fermions. Now, just to distinguish, I denote them by etas, not psi, another Greek letter, never mind. So we would like to introduce a coherent state that is defined as an eigenstate of A alpha with its eigenvalue eta alpha. Okay? And if we can do it, then we can find the conjugate related to a dagger, and we can do everything we did for the bosons. But we see that there's a problem, because if I now have, I take two operators, A alpha, A beta, with let us assume that alpha is different from beta, because otherwise it's 0, right? And now let's apply a pair of operators on the coherent state. Okay, so we'll do it carefully, just following the definition. I first apply A beta, okay? And I get eta beta times eta, the same state, and eta is a number, so I can move it around, and then I apply A alpha on eta, and I get eta alpha, right? So I can write it like this. Okay. However, A alpha A beta is equal to minus, okay, this equals, the same thing has to be equal to minus A beta A alpha, where here I first apply A alpha, right, so I get eta alpha, eta A beta, and now and eta alpha is just a number, A beta acting on eta gives you eta beta, sorry, I forgot the minus sign. Okay, so minus, we do it slowly, eta alpha, eta, and then minus, eta beta, eta alpha. Right? Now, this equals that, right? So this is an equality. So what we got is that under our definition, this has to be equal to that, right? But the etas are numbers; they're no longer operators. So there's a problem, because to satisfy this, we must require that eta alpha, eta beta equals minus eta beta, eta alpha. So the same anti-commutation feature is converted into the eigenvalues. Okay, and that's a problem because if we want to understand these etas as complex numbers, they are commutative, right? You know that any number, complex numbers, real numbers, they are commutative objects. So how do you solve it? So it doesn't work, okay? Unless,
or it's just zero.
unless, well, okay, there's another actually special case of that. So we know that A alpha acting on a coherent state gives you something different from zero, right? Because it's just an eigenvalue. It's different from zero. But if we apply it twice, we know that the right-hand side, the left-hand side is zero, the right-hand side has to be zero. So a special case of that is that eta alpha squared has to be zero. And in fact, eta alpha to any power greater than 1 has to be zero. These are not regular numbers. I mean, if there are such things, then they cannot be regular complex numbers. So it looks like this suggests that we cannot extend the coherent state description or the coherent state path integral to fermions. And it makes sense because fermions are not meant to describe coherent states, right? I mean, they like to be individuals. But fortunately, sometime in the 19th century, there was a mathematician named Grassmann, and for whatever reason, I don't know what was the motivation originally, but he defined an extension to the number, to the family of numbers, just like we extend from real numbers to complex numbers. He invented this thing that is called Grassmann algebra. So what is Grassmann algebra? It's a new set of numbers. Okay, you can think of it really like an extension of the numbers that you know, but they have this funny feature, and it's actually this one. Okay, so that they are anti-commuting, or they give you a minus sign under any odd permutation. Okay. Also, for any Grassmann variable to the power n, with n greater than 1 is 0. Okay. Okay, so this is called Grassmann algebra. And then actually every arithmetic or mathematical operation we want to do with them will be different because of these funny features. And actually, to some extent, it will give us simpler calculations. Okay? They're very strange, but it gives, you'll see why in a second. Let's see, what else we need. So first of all, when I say algebra, so you need to define a set of variables and some rules. Okay, that's generally the case. These are the rules. Okay, so I have my set of Grassmann variables. And this is what they obey. That's the basic. Okay, but what if I also have, just like when I extend the real numbers to the complex plane, I can also take a complex number and multiply it by a real number, right? What do I get? I get once again a complex number, right? So in analogy, we can also somehow have to tell what happens if I multiply. So this is what happens when I multiply Grassmann variables by themselves. what happens, and now I also have some set of complex numbers. Okay, these are just regular complex numbers. If I look at the combination C alpha, eta alpha, this is a Grassmann variable again. Okay, so multiplication by a complex number leaves it within the family. Yes?
C is an operator? Or?
No, it's not. Nothing is no operators. No operators.
Complex number.
It's a complex number. Okay. Eta is also not an operator. I should stress it. But it's a Grassmann variable. It's not a regular number. So C alpha is actually because C is a regular complex number, which is commuting under any with anything else, any other number. So we have this. So C alpha and eta alpha commute with each other. So, but if I have, if I take, I don't know, C alpha, eta beta, then the etas will anti-commute, but the complex numbers will commute. Okay? So I can put the C anywhere I like, and there's no minus sign. Yes?
How are you going to use this new kind of number for usual continuous functions like exponent?
We're getting there.
Because
That's exactly
really strange.
where it's actually very cute. Okay, so it's actually yes, because that's what we want.
Yeah.
Remember what our goal is. Our goal is to use this to write a path integral. So we need to know how to write a function and how to write integrals, how to do integrals and how to do derivatives. Okay. Okay, so we need a set of rules, but first I want to say that if you take Grassmann variables and complex variables together, they form a closed algebra with well-defined rules. And what else I need to do? So here comes functions. So how do I define a function of Grassmann variable? Okay. We know how to define a function of real numbers or of complex numbers. What is the definition of a function? The general definition is, or one way to do it is in terms of a Taylor series. Okay? Let's assume for simplicity that it's an analytic function. We don't care about funny things or singular, just, an analytic function, an exponential, a polynomial, it doesn't matter, okay? So, any analytic function has a Taylor series, right? So, it's, this is generally true.
With just two terms, right?
So we can expand it. We can expand any function near x equals 0 with this is f, the nth derivative at 0, x to right. This is a general Taylor expansion. Now, and if I have a function of many variables, I have an expansion in terms of the complex derivatives. Okay, so generally there is, if I'm looking at, I want to define, let's first do it for the most general case. I have I don't know, f alpha 1, alpha 2. Okay, I have a function of many Grassmann variables. I want to write it as a Taylor series, but it's a Taylor series of actually, I'm a little sloppy here maybe, but you have the nth derivative, but the derivative can be generally a sum over all derivatives to all variables, right? So so here you have something like df to d eta 1, d eta 2, okay, n times, okay, at all that calculated at 0, where all the variables are 0, so this is just a concept, and now you have, that's the important thing, I have eta alpha 1, eta alpha 2, product up to, so eta alpha n. Okay, you have something. Okay.
Shouldn't be power n.
So this is to the power, this is when you have more than one variable, the nth power is all the combinations of, actually I'm a little sloppy here because you have all the summation over, here I also have summation over all the configurations of the, okay, all the sets of alphas that have overall n indices, but now that's the thing. So because of this, or actually because of this, each variable can appear only once, okay? So if I have a function of, let's take a simple example, if I have a function of 2 variables, and I go to second order, I only have the cross terms, okay? But why go immediately to 2? Let's go to 1 variable, okay? A function of a single Grassmann variable, what is the Taylor expansion? First there is f of 0, that's the 0th order, plus, what's the next order? First derivative at 0 times eta. What will be the next order? 0. Actually everything else. So this is the Taylor expansion, and it's not an approximation. That's the beauty. It's not an approximation. Okay? That's great because, for example, if I have a function like e to the a eta, where a is some complex number, this is, what is this? Let's see if you understood the trick.
1 plus.
It's 1 plus a eta. That's it. Okay? All right.
Again, if I get that, then why no higher orders again?
Because all the powers of eta, except for 1, okay? This is actually the crucial. Okay? So you can have a function of high order, high order, but they have to be distinct in the distinct variables. Okay?
So it will just be for distinct variable, but still only second.
Yes. So if you have 2, then only the cross terms of the second. That's right. And if you have I don't know, n variables, you can have a term eta 1, eta 2 up to 1, but no eta 2, no other, just one term, just the cross term. Okay? So everything becomes simpler, but and for our purposes, actually, this is what we need. Okay? For everything we do, this is what we need. But now there are additional rules. So we have we have algebra rules like what are the mathematics we need? We have multiplication, we know, okay? Addition is like 3, okay? Addition is 3, yeah? Taylor expression, no, division is, no, we don't need it, but we know how the next thing we need to define is a derivative with respect to a Grassmann variable, okay? A derivative, so I want to define the operation here. D eta, let me call it D eta alpha, eta beta. What is this? So if eta, let's first think in a simple way. If beta and alpha are different, it's 0, right? Because you take a derivative of a function that does not depend on the variable, then it's 0. If beta equals alpha, it's like the derivative of x with respect to x, it should give you 1. So, okay, so it is a delta. This is actually a property that resembles regular numbers, okay? But now let's see if you can tell me what is this. So suppose I have the following. Okay. What is it? Okay. Let's do it. So if there were regular numbers, you'd say, of course, and of course, this is alpha is different from beta. Otherwise, it's trivially 0. Okay, right? So alpha is different from beta. Otherwise, it's already 0, so there's no question. But alpha is different from beta, so naively you say, beta is different from alpha, so why don't I take this and move it here and it acts on beta?
You can change the minus sign.
But that's dangerous. So let's be careful. We leave the derivative the way it is, and we exchange it. This is always an identity. We exchange it, we get a minus sign, right? Okay. And now I'm in so let me just rewrite it. The minus sign I'm allowed to move. That's fine. So I have a derivative, this derivative, and then eta beta, but this derivative give me 1, right? So the result is minus eta beta. Okay? This identity actually suggests that I could have done, instead of switching the etas, I could have moved the derivative over here, but with a minus sign. Okay? So in a sense, when I write a derivative with respect to eta, okay, a single derivative is like another odd creature in terms of the powers of eta. Okay? Right? So what I'm saying is that also derivative with respect to alpha and with respect to to a Grassmann variable eta alpha and another Grassmann variable eta beta are also anti-commuting. Okay, they're also anti-commuting. So in short, any any Grassmann variable or a derivative with respect to a Grassmann variable is an odd. It has is anti-commuting with the address. And there is no point in talking about the second derivative with respect to eta because it's 0. Okay. Okay. So we only have linear functions. Okay, that's all. Okay, very good. So that's another important rule. Now for another rule that we need, and it's very, very important. We know how to take derivatives. Therefore, if we can take a derivative of this, we can also take a derivative of any function, right? What is the derivative of so let me do it. The derivative with respect to eta of f of eta is, let's do the calculation, it's a very simple one. The first term gives you 0, right? It's a derivative of a constant, it does not depend on eta. First term is 0. The second term gives you okay. Okay, so it gives you just a constant. Okay, so we know how to do the derivative of any function. All we need to know is its first derivative. That's all. Okay? And the result, interestingly, the result is the derivative of the function at 0. Just a number. Now, we also want to be able to do the inverse operation. What is the inverse operation of a derivative? Integration. Okay? So now I'm going to write definitions, okay? And there are really definitions that are consistent in the sense that if you do an integration of the function, you get, so you expect to get the, how do you call it in English? The function קדומה. How do you translate it to English? It's the
Formal.
What?
Formal?
So it's the function of which that you have to.
Proceeding function.
Yeah, proceeding. Thank you. Right. I somehow forgot the name. The proceeding function. So, in order for all this to be consistent, this is how I need to define my integrals. Let me write it here. So, integration over eta gives you 0, and you notice that I'm not writing limits because there's no meaning to it. Okay, there's no meaning because eta is this funny object that changes sign. Integration over eta is once again an odd. It's actually, if you want to think of it, it's like summing over all possible values of etas, but anything to linear order can have its minus sign, right? So the result when you sum over all possibilities is you get 0. Okay, so this is just a definition.
It can't really be negative, right? Because
Why not?
physically
I
speaking.
mean, there's no meaning to saying that it's positive or negative because
but
it depends on the order where you put it in a string of other Grassmann variables.
Like
Okay.
complex numbers, you cannot say.
Okay. In fact, you can think
Or
of
it's
it
only-
as a kind of a Boolean algebra in a sense, because any odd combination is is if you sum over all possibilities will give you 0. Any even combination can give you something finite, and therefore, so if you look at this, okay, so the integral over eta, this is like an integral d eta over 1. This is an integral over eta. This is 1. Okay? If eta is the same eta, of course.
Yeah.
Okay?
But if you take a derivative from the answer, you should get the same thing that you have inside the
That's
integral, right?
Yeah.
So in the first case, you should
Right. So let's do the following. So if I take, so first of all, these are the rules, okay? These are the rules, and now let's do an integral over a generic function, okay? Any function. Okay. This. But we do want to just to move this and okay. All right. So an integral d eta of an arbitrary function f of eta is equal to, let's plug in the Taylor expansion. Okay. Now the first term will give you 0. The second term will give you f prime times the eta is 1. Okay? So, what did we discover? An integral over f gives you f prime at 0. A derivative gives you the same. Okay? So, an integral and the integral and the derivative are the same. And that's true for any complex function you can think of. Now that's actually amazing because it's so much easier to compute the derivatives than integrals. So in fact, integrations are very simple. Okay? And now we can also generalize it to a multivariable function because you just need to keep track of the order. Okay, right? So if I'm writing, so for example, I have an integration over eta alpha, eta beta of, let me write it like this, eta alpha, eta beta. What is the result of this integration? Okay, I have to be a little careful, right? Because, let's do it carefully, I switch this and this, then I get a minus sign. But after the minus sign, I have an integration. Let me leave the integral sign here. So I will get, minus integral d eta alpha, d eta beta, eta beta, eta alpha. But now I solve this integral. It gives me 1. And then I'm left with the other integral, and altogether it gives me 1. Okay? Whereas if I have
minus
just...
1, no?
Hmm?
Minus 1.
Sorry. sorry, yes, you're right, -1. If from the first place I put the beta on the left, it will give me +1. Okay? And so on. Okay, so you see, in fact, with these rules, you know how to solve any integral. And now, let's accept our rules, and now go back to our coherent states, which is why we defined it. We want to define coherent states, and just like what we did for the bosons, we want to be able to write them in terms of the second quantization operators. And this is how they look. So again, I'm not going to prove it, because you'll do it in your homework, but it's a very easy calculation, okay? So I think this we can erase now. Okay. So these are the fermion coherent states. Again, they have to obey. So let me just write down an expression, and a calculation, a careful calculation can prove it. It's actually very similar to the bosonic version, but there is a minus sign. All that acting on the vacuum. Okay. I claim that this is the answer. How do I know? Just do the calculation. Take an arbitrary annihilation operator acting on this. You will get the same thing times eta. Okay? Exercise, homework exercise. Okay? And by the way, how to do the calculation? Expand it to a Taylor series. Take into account the fact that it actually has only linear order, right? So it's actually very simple. Okay? All right, so we can define the coherent states. Actually, if I compare them to the bosonic coherent states, the bosonic version was, which we call the, I don't know, psi, okay? Coherent state was this is for bosons. What's the difference? Two differences. First of all, these are complex numbers. These are the Grassmann variables, but there is another difference. There's a minus sign. Okay. So to be completely general, just using my notation of the zeta, which is plus for bosons and minus for fermions, I can write a general expression for a coherent state. Let me call it psi, is e to the zeta sum over alpha, psi alpha, alpha dagger, up to okay. This is an expression that is valid for both bosons and fermions, but the interpretation is that for fermions, the operators are, so this zeta is minus, and these are fermion operators, these are Grassmann operators, okay? So this is very convenient, and you start to see that the structure is is not very different from what we got for the bosons, suggesting that we will be able to copy-paste our derivation of the path integral, and in the end, we'll get something very similar, but there will be some zetas, okay? And that's almost true, but there are some subtleties also. Let us write the conjugate. So what I wrote here is the state, the bra state. I want to take the conjugate of this. With your permission, I'm erasing this. Okay. So I just take the this is okay, and here I have to be careful because so before, remember, I for the bosons we had the complex conjugate of, the Hermitian conjugate of this thing. Now we also have to keep track of the order, okay, of the eta and the a, because every interchange is picking a minus sign, okay? I should also mention that this is another rule that is kind of, so if I have, if I'm interchanging a Grassmann variable and an operator, this is also anti-commutative, okay, with alpha different from 0. Okay? Okay, so the conjugate of this is actually e to the shall we write it as okay? Okay. So we just take the Hermitian conjugate of this is just exchanging the order of everything, right? That's the definition of Hermitian conjugation. So I have something like this, okay, and it's acting on the vacuum, okay, or if you like this I can move here. Okay. It doesn't matter. Okay. This is just Hermitian conjugate. Actually, no, it's not right. That's not the way to write it. Okay?
I have a question.
Yeah.
How do you find complex conjugate of
Very good.
Grassmann?
You can't. It's not a complex. So it's
the same.
I call it a eta bar, but
the
it's
same.
not. It's not a complex conjugate. Why it cannot be a complex conjugate?
Just different numbers.
Because let's go back to if you have a complex number, psi bar psi is equal to absolute value psi, right? For Grassmann variables, it cannot be because this is 0, right? Because absolute value is positive definite real number. Right?
Yeah, what happens if
So you cannot make any combination of Grassmann that will give you.
I was going to ask the question
Yeah.
about the inner product. Like, how would you get the inner product if we're using Grassmann variables? Because it would
Okay,
kind
so
of break
that's
down.
what what I'm saying is, so I know how to write an inner product of coherent states, okay? And I'm going to write it in a minute because we really need it. First, I know how to write the Hermitian conjugate, okay, and that's this. But now I can rewrite it in the following way. Let's leave the order the same, but now I want to switch the order of the A and the eta bar. But eta bar is also a Grassmann variable, so interchanging this and this changes sign. So this will give me a plus e to the alpha eta alpha bar A alpha.
It's come from the commutation relation?
Yeah, the anti-commutation. Okay? So that's also a legit operation. And now, having that, I can now compute the and there is another identity I want to write. So let's see what happens if I take this. This is a definition of the coherent state, right? This is just a if you like, from this definition you get it, but this is really the definition. If I just take this line and I do Hermitian conjugate, I get eta A alpha dagger, right, equals eta bar. Okay. Now, okay, and now I take this definition and this definition, and I compute the inner product. So for example, I have some eta prime and eta. What is this? Okay. Let's do it. So I have a 0 here, and then I plug in the let me call these indices alpha primes, bar A alpha prime, e to the sum over alpha A eta alpha A alpha dagger, 0, and now what I need to is to compute this stuff, and then I said it gives me some number that is actually even under interchange, so I can take all of this outside of the inner product, and the inner product of the vacuum is 1. Okay, right?
Why you can take out?
Sorry. 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 I have to. Let's do it carefully. I have to apply it on the vacuum. Okay. Then this will actually. What did I? Yeah. Okay. So you need to. So the way you want to sorry. Yeah, right. That's the trick. So you take this, you expand it to a Taylor series, and then you use the fact that this is a coherent state, right? So it's actually. You can use this identity because what is the expansion of this? It's just 1 plus all the linear terms, right? Okay, so So this will, so if you do the calculation, and again, I think there will be, this is either a tutorial or a work. This is what we get. In the end, there will be a sum over eta prime alpha bar, eta alpha. And if we go back to the bosons, you see that you got exactly the same expression, except for the fact that eta bar is not to be understood as a complex conjugate. It's another Grassmann variable. That's what it is. Eta and eta bar are two distinct Grassmann variables. That's the only way to understand them, because otherwise the combination eta bar eta will be 0. Okay? So eta bar eta can be non-zero only if eta bar and eta are different Grassmann.
Why do we need to keep track of bar, even though?
Oh, because
it's
it's there, and if we write, so for example, if we write so the inner product depends on the bar. The Hamiltonian, if we convert, so when we do our path integral, everything will involve, just like for the bosons, a combination of etas and eta bars.
Yeah, but we said before that we cannot really define what is complex conjugate of this
No, what I
Grassmann
said,
variable.
let's be exact, what I said is that it cannot be interpreted as a complex conjugate, but it is just another Grassmann variable, and I know how to do the integration. For example, let's take a concrete example. If I have something like this, okay, what is this? Something that looks like a Gaussian integral with Grassmann variables. A is a complex number, okay? I know how to perform the integral.
Take
And the idea is, once again, just to take this. This is a function of two variables. I have to expand it to linear order because, so yes, in this case it's the linear order. And what does it give? There is already an important formula, which you can very easily prove. Okay? Okay, so it's actually, if you remember, sorry, there is a mistake, minus, okay? Okay?
So what you're saying is that there will be no cross term, right?
What do you mean no cross term? So
When you
what?
expand it, you have linear sum.
Actually,
at
let me
the bar,
just
and
a
then
minute.
at
Let me make sure. Yeah, I wrote it in the right order. Yes. What?
So there will be no term eta bar times eta
Yes,
because it's 0.
that's right. Yes.
So, but from
Yes.
my perspective, if you say that, you mean that that's just the same complex conjugate as we define for complex numbers.
No, actually not, because notice that what did I write here? It looks like a Gaussian integral, right? If etas were complex numbers, what is the result of a Gaussian integral? We actually use the generalization of that. So for complex numbers, d psi bar d psi e to the minus psi bar a psi, which is a simple special case of the Gaussian integral we worked before. This is equal to pi over a, right? So if I put the pi here, I get 1 over a. For Grassmann variables, it gives you a in the numerator, not the denominator. Okay? So it's just different, and you need to stick to the rules of what is an integral and just work them out, and everything is consistent. So this is an identity. This is a Gaussian integral for Grassmann variables. And if now I have something that is, there are many Grassmann variables, etas and eta bars, it can be generalized to a product of integrals, and you get a formula very similar to the Gaussian formula I wrote before with the matrix A, but actually let me write it down. For bosons we got, or for complex numbers we got that d psi bar, d psi over pi, let's put the factor of pi here, because remember this is how we defined our differential, e to the something like this. And now psi is not just a single variable, it's an array of psi alphas, okay? Here psi is psi alpha 2. Okay, and this is a scalar, this is a general matrix, okay? So for complex numbers, we got that this result is a determinant of a to the minus 1, right? For fermions or for Grassmann variables, d eta bar d eta with no pi, the same formula, okay, the same functional form, it's an exponential of minus, eta bar, A is a matrix, in general, it doesn't have to be diagonal, that gives a determinant of A itself, not the A minus 1. Okay. So if you want to be more general, again using this index zeta, if I have a functional integral, actually this should be replaced by a capital D, because this psi is okay, this is be a little more careful, because I define psi to be not a single variable but a product of all alphas and so on, and this is it as well. So let's call this differential. No, sorry. What I want to write is, let me define this to be a product of all alphas of d eta alpha bar, d eta alpha. Okay, just like what we defined for the boson, with no factor of pi. Doesn't come in, no pi's. And then this is going to be d of eta bar eta. So this thing is, for either kind of particles, can be written as it is a determinant of a to the power minus zeta. Okay? So if they are bosons, it's -1. If they are fermions, it's +1. It's just determinant. Okay? So these are mathematical formulas, but you already see that why we need them. Because if we want to write a partition function of non-interacting particles, we can use them and get a definite result. Okay? All right. So actually, let me just write down. Let me see of the time. Okay. Let me write down a few equations. Let's accept them, and then we'll see how we do the path integrals. Okay. Okay. So let me leave this here. So first we have this captures both type of particles. This captures both type of particles. And to measure this.
Can I ask a question?
Sure. Yeah.
Shouldn't be in this integral in the blue box
Actually,
left
yeah,
one.
this
This
one.
one. Yeah. Shouldn't be at the bar prime.
No, this is the same eta.
But
Eta bar, again, eta bar is a different variable. So the combination eta bar times eta is not 0.
So it doesn't matter if there's prime or not.
Yeah, the prime, it matters only if you have eta and eta is 1 and eta, okay? Eta bar is, you can think of it as a prime.
Is there a proper mathematical definition for eta?
Yes, this is the Grassmann variables. I'm giving you this is a brief introduction, okay? But it is defined in such a way that everything is consistent.
No, but like a definition that is functional, like a function which gives the value of eta for each situation.
What do you mean? Eta is a variable, right?
Yeah,
And we know how to write
yeah, but it's not really
any function of eta.
yeah, but it's not a variable in the strict sense of the word because it depends on the situation in which it is used. So it does have.
No. No, again, it has a strict rules of arithmetics and algebra and how to do integrals, how to do derivatives. It's just like in regular numbers, okay? But you have to keep track of the order. And every exchange gives you a minus sign. That's all. Okay? And any square, or it cannot appear twice, so all the functions are linear. It's actually very simple, but yeah. Okay. Okay. So in the end, something like this. The right-hand side is a regular complex number. It can even be a real number. Okay. It's just a regular complex number, and actually, if you look at any physical quantity, by the way, it's the same thing with complex numbers. Any physically significant quantity will be given by an expression which involves real numbers. Guaranteed. Okay? But on the way to get to it, you have to work with these variables, and the only thing, it's really doing calculations using a small set of formulas that are all consistent with each other. And if you have many variables and you do exchange, remember to put your minus sign. That's all. Okay? All right, so let me just write here a few useful formula. This is one, okay? This is for Gaussian, actually let me write it, the more general version of it. So this integral yeah. Just write it only for the formulas, so e to the minus eta bar sum a eta. Now I want to extend it to a more complicated function. So this alone will just give you the determinant of a. But now I want to extend it. I'm adding here eta bar v plus v bar eta, where this v bar, v is a regular complex number. Okay, so v belongs to the complex, and eta and eta bar, they are Grassmanns. Okay, I don't know how to denote it. Okay, these are Grassmanns, but v is just a complex number. Okay. Okay, so the result of this integration is there is a determinant of a, right? But there is also an exponential factor that looks like this. It's v a minus 1 v. Okay. Yeah. Okay, and notice that this is already an expression that we got rid of all the Grassmanns. We just integrated over them. This is a very useful formula. What it reminds you is like a Gaussian integral of regular numbers or complex numbers, where in addition to the Gaussian factor, you also have a linear coupling to a field, right? Something like that. And you know it's a generalization of this. Equals, okay, up to, okay, this pi over a times e to the b square, something like that, right? You know this formula. This is just a generalization of it, where here v is a vector of complex numbers. Okay, so actually v is not just a complex number again. Both eta and v are actually vectors. Okay? But the components of this are Grassmanns, and the components of this are just complex numbers. Okay?
Just the non-interacting part plus
Some,
coupling,
for example, coupling to
magnetic
some
field.
magnetic, yeah, you can think of it like that. Although, actually, to be honest, this is not something you find in any Hamiltonian. There's no Hamiltonian that, oh, actually, no, it's not true. Because this is a Hermitian conjugate, Hermitian combination, it can appear. Okay? It's a funny thing, but it can appear not in a standard, one-body thing, but we are going to actually, next week, we are going to make use of this formula and so on, okay? All right, so, okay, good, great. Now there is an additional formula, very useful formula, which is, again, a Green's function. Let's write it. Eta alpha, eta beta bar. Okay, this expectation value, if you like, it is a Green's function. This is the definition of a Green's function for fermions, and it gives you a -1 alpha beta. Okay? Or let me be a little careful. It's a -1 alpha beta. Okay? A -1 is generally a matrix. Okay? So it is actually very similar from what we got for the bosons. Okay? And so again, whenever we have a quadratic theory, we can compute expectation value of a pair of etas. That's what you get. And if I now, let me ask you this, so now I have a generalization of that. I have eta alpha 1, eta alpha 2, blah, 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 and then I have some beta 1, beta 2. Okay? What do I get when I take the expectation value? Or how do I do the calculation, actually? So, one can prove, we're not going to do it, but it's the same idea that we saw a few lectures ago. You can use weak theorem to decompose it to all the combinations of pairs. And each pair, you know the result, right? But for fermions, you need to keep track of the order, right? So when you do the contractions, you can have a Hartree and Fock, depending on how many, if the the number of exchanges is odd, you pick a minus sign, okay? And the expression for this is, in fact, just, and again, I'm assuming here, a quadratic action, otherwise it's not true and you don't know how to compute it exactly, right? I really stress it. This too, if you like. So this is given by the sum over all permutations, zeta to the p, or sine of p, so it's just a minus sign if it's an odd permutation, times a -1 of a alpha permutation of beta, a -1 alpha 2 permutation of beta 2. Okay, product of all the possible pairings, and just like what we did when we did the Hartree-Fock, you do contractions. You contract pairs, and each pair is given by this, and you get an expression. Generally, it's complicated, but if you just have 4 operators, like a typical interaction, two-body interaction term, it's actually very simple. And once again, you get the Hartree and the fork, etc. Okay? All right, so the last part, an important part, is why did we bother with all this? I want to write a partition function of fermions as a path integral. What do? Repeat all the steps we did before for the bosons. And since we only have 15 minutes to the end of the lecture, I will do it very briefly. I'm not going to repeat it. I just want to point where are the pitfalls, where do we have to be careful, okay? Okay, so let's just first write the partition function from the definition. Okay, this is what we want to compute. Beta is the inverse temperature, and we write it as a sum over, I don't know if I want to call it, let's call it n, that's fine. E to the minus beta h n, and here h describes is a Hamiltonian, a grand canonical Hamiltonian of fermions, okay? I'm not even writing it. And here are some set of complete bases, okay? So N is just a complete basis of the many-body states. For example, Fock states, okay? Okay. I remind you how we did the path integral. The trick was to take this expression and put here a resolution of the identity. And the resolution of identity I write in coherent states. What is it? For fermions and bosons, because we saw that the inner product has exactly the same expression as in the bosons, the definition of the inner product is, the resolution of identity is, yeah, so the resolution of identity is integral over I want to be a little careful. Yeah, so it's essentially this. Okay, let me write it a little more carefully. So it's a sum over alpha, eta alpha times. Okay, where does this come from? Just like for the bosons, the inner product eta with itself is not 1. It cannot be normalized. It's actually e to the sum over alpha, eta alpha bar, eta alpha. The only difference from bosons is this cannot be written as eta absolute value square. It is just 2 distinct variables, okay? But then, if I want to introduce a resolution of identity, I have to divide by this factor in order to get rid of this non-trivial overlap. And I just remind that this is defined as a product over all alpha of d eta bar d eta. Okay? So that's the definition. Okay, and here I keep track of the order because the order is important. Okay, whether you write eta or eta bar, if you switch, you get a minus sign. So be careful. This is the resolution of identity. When I plug it in here, what will I get? Let's do it very quickly just to see where we're heading. I'm going to get, I will take all this integration outside, but I want to get rid of the quantum states by making, so here I have, of course I'm going to have this operator sandwich between eta and n, where n is a Fock state. Okay, it's a Fock state, but eta is a coherent state, and this is multiplied by, I'm going to get something like this, eta n, and then eta e to the minus beta h, n, okay? Okay, and here I'm summing over n, and I integrate over eta, etc. Now, what do I want to do? What did we do for the bosons? I remind you. We said, okay, this is some matrix element of an operator, but this is just it's just a number, right? It's an inner product of a coherent state and some Fock state. Okay. It is just a number. Because it was just a number, in that case it was a complex number. I can take it and switch it, and take it and switch it here. And if I do it, now I will get a sum over n, and with the projection nn, and this is resolution of identity, and I get rid of the n's and remain only with the coherent state. Now for the fermions, I want to do the same, but I have to be careful. Why? Because this number is not a regular number. It's some combination of Grassmann variables where each Grassmann variable appears only once, right? Remember, only linear order. This also depends on Grassmann variables to linear order. So if I'm switching, I'm moving this here, I'm always interchanging some eta alpha with some eta beta, and what happens when I interchange? Minus sign. So the only difference from the bosons, but it's an important difference, it's actually a very big nuisance if you want to convert it to a numerical algorithm, by the way, which is called the sign problem. Okay, if you have heard. Okay, so what I'm getting, to cut a long story short, is I will get a minus, write it like this. So after I get rid of the resolution of identity and all that, I get that the partition function is, okay, let me call it psi and not eta. Okay, just that we keep our notation for the fields uniform. And I have this exponential, which I write as psi bar psi. Okay, just for a shortcut. And now I have minus psi e to the minus beta h psi. Okay, so for the bosons, I got the diagonal element, which then I do the path integral thing, I introduce steps, blah, 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 blah. But for the bosons, where I didn't have this minus sign, when I look at the imaginary time axis, I go from 0 to beta, I do the time steps, but I return to the same psi. That was for the bosons, right? So for bosons, we got the boundary conditions where that psi of 0 was equal to psi of beta. For fermions, all the steps in the middle have the same structure, but I start with a psi and end with a minus psi. So the boundary conditions are anti-periodic. Okay? So for fermions, I get the path integral in the end will look exactly the same, except for two things. First, the interpretation of the psi's is that they are Grassmann variables. We have to do Grassmann integrals, and the results are different, right? We have the determinant in A and not A in inverse, so on. But not less important, we have different boundary conditions. That psi of 0 is minus psi of beta. Okay? So now, for the bosons, we did a Fourier expansion in terms of the Matsubara frequencies, and we used the fact that it's a periodic function to get integer multiples of the basic period, or the basic frequency. Here, we have to obey anti-periodic boundary conditions.
So we have not 2 pi, but just pi.
Exactly, or if more generally, an odd multiple of pi. Yes, exactly, that's exactly right. Okay? So let me just write the bottom line and we'll stop there, because we are all tired. In the end, for fermions, what you get is that Z is something that you can implicitly write in exactly the same way, except, and this actually will have exactly the same form with psi bar, d tau, everything is the same, but if you convert, but the boundary conditions are that psi 0 is minus psi of beta, and of course these are Grassmann variables, therefore the result of the calculation will be different. But when you convert it to the Matsubara frequencies, and it's again useful to do it because you have a time derivative, okay? You can write it as a Fourier expansion. Psi of tau is 1 over square root beta, sum over n, psi n, e to the minus I omega n tau. Looks exactly the same, except for one thing. Omega n is given by 2 pi it's given by pi times 2n plus 1 times t. Okay, there's an extra one, or it's half if you like. It's when you write it instead of integer multiples of 2 pi, it's half integer multiples of 2 pi. Okay, and that's the only difference, but it does change the analytic structure of the function, because in the end, when you're going to get these factors of I omega n in the denominator and all that stuff, it will look exactly like in the bosons, but this fact will change the analytic structure of the functions in the complex plane, and will give you, of course, instead of a Bose-Einstein factor, you will get a Fermi-Dirac. Okay?
Change in the sign of the denominator.
Yes. Eventually,
Minus
when
the
you
plus.
do it carefully, blah, 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 you'll do it in the, I hope in the tutorial of SAR next week, you'll get Fermi-Dirac. Okay, so the mathematics is actually the same, and you just need to keep track of these differences. Okay. So next week we are going to see how we deal with interacting fermions and take advantage of this formulation. Okay. Have a good weekend.
אנחנו אמרנו שזה שווה בהכרח לבנות.
כן,
עכשיו,
זה הרעיון.
העניין הוא שזה תלוי בכמות בעצם